Marko Cetina, beginning faculty in the Department of Physics and Department of Electrical Engineering and the Duke Quantum Center at Duke. I have been very involved in building and running quantum computing systems based on ytterbium ions. And the system that I'm showing here, we are running it remotely from a control room in the Duke Quantum Center. And we're showing live a picture on a CCD camera of 23 ytterbium plus ions that are emitting fluorescence during laser cooling. So each of these dots is one single ionized atom of ytterbium, and we are using these to perform quantum computing. Each ion serving to store 1 qubit of quantum information. The spacing between these ions is about 3.7 microns, and we can position them by changing the electric potentials that is applied to the trap that traps them with an accuracy of plus minus 50 nanometers. We use that to align each of these ions to one individual laser beam that we use to manipulate the qubit states and also to create entanglement and perform gates between the ions. Thanks to the isolation provided by RS4000 tables with air-floated legs, we can maintain the operation of this system with relative alignment accuracy between the laser beams and the individual atoms of plus minus 50 nanometers, even while traffic is happening outside, including trains passing right outside the parking lot. You can see here an experiment that demonstrates the quality of the alignment between the ions that we trap and the laser beams that we use for addressing. Here, we are holding one ion out of the chain of 23, and we're moving the ions from minus 1.5 microns to plus 1.5 microns. And while doing that, for each of these locations, we look at the effect of the laser beam that we use for manipulating the qubits on that one ion. Here measured as the fraction of the population transferred from one qubit state, the 0 state, to the other qubit state 1. And we map out, by doing that, the shape of our addressing laser beam. And you can see here that we can position the beam relative to the ion with plus minus about 50 nanometer accuracy, as demonstrated by a very nice fit of the obtained data to a Gaussian profile of a laser beam. The reason that we can achieve this remarkable alignment accuracy between our addressing control laser beams and our ions holding the qubits is the excellent vibration isolation that we have in this system, thanks to the RS4000 tables with air cushions in the lab. This here shows the performance of an entangling quantum gate performed between ion number 3 in the pictures that you had seen before and ion number 20. In order to create entanglement between these two ions, we shine two of these individually addressed laser beams, one on each ion, to perform a so-called quantum XX entangling gate. As a matter of fact, in this experiment, we perform 3 such gates in sequence. And following that, we perform some additional manipulations on the individual qubits that let us measure how well entangled these two qubits are. For the experts, this is a parity fringe and parity measurement on the entangled state. Amplitude of this sine wave that I'm showing here characterizes the quality of the entanglement. And the fitted value here of 94% corresponds to entanglement to the fidelity of this state that we prepared in excess of 97% after 3 gates. So about 1% error per gate in a system of 19 qubits between the 2 qubits that are most separated in space, demonstrating quite strongly the very high connectedness and high fidelity of the trapped ion architecture that we have at DQC.